In the previous lecture segment, we solved the problem of building a topless rectangular box with volume 32,000 and the smallest possible area. And we found that the dimensions that minimize the area are where the horizontal dimensions x and y are equal to 40 and the vertical dimension z is equal to 20. And you can work out the area if you like. I'll skip that. And we also saw that the Lagrange multiplier lambda is equal to 1/10. Now what's the significance of that? So far, in Lagrange multiplier problems, we've used the Lagrange multiplier as a tool to solve the problem, and then we've just thrown it away at the end. But it actually has meaning. It's relevant to the following question. So suppose that we want the volume of our box to be 32,001 instead of 32,000, always minimizing the area. How much more area do we need? So when we increase the volume by 1, how much do we have to increase the area? Well, we could do the whole problem again, putting 32,001 into the constraint equation, but there's a quick way to approximate the answer without doing any work. And the answer is approximately 1/10. And this 1/10 is just the Lagrange multiplier lambda. So the meaning of lambda is it's telling us how much the minimum or maximum value of f changes as we vary the constraint. So here's a general statement of what's going on. So the general statement is let m of k, this is a real number, denote the minimum value of some function f subject to a constraint g equals k. This could be in any number of variables. Okay, so this works just as well for minimum or maximum, but let's stick with minimum for definiteness. So m of k is the smallest possible value of f when g is equal to k. And there's a little technical caveat, which was we have to assume that the gradient of g is not 0 at this point, so that Lagrange multipliers work, and also that this minimum is unique. There's only one point where f takes its minimum. Then, as we vary k, as we vary the constraint, the derivative of the minimum value m is exactly equal to the Lagrange multiplier. So let's prove this. So let's draw a little picture. So here's a level set g equals k. Here's another level set, say where g equals k plus 1. Here's another level set where, say, g equals k minus 1. Now, what we're going to do is we're going to let r of t be a parameterized curve such that r of t, or r of k, let's say, is the point on the level set g equals k where f is minimized. So g of k is r of k is some point over here on g equals k. This is where f takes the minimum value on g equals k. And f takes the minimum value on g equals k plus 1 at some point r of k plus 1, and f takes the minimum value on g equals k minus 1 at some point r of k minus 1. And of course k could also be some number that's not an integer, and we put all of these points r of k into this parameterized curve r of t. Okay. Now let's look at the derivative with respect to k of m of k. Now by definition, m of k is equal to m of r of k, because r of k is the point, ddk of f of r of k, because by definition f takes its minimum on the constraint set g equals k at the point r of k, and so that value of f is what we're calling m of k. Okay, now by the chain rule, this is the gradient of f evaluated at that point. I'll skip that from the notation. dot r prime of k. Now by the Lagrange multiplier equation, the gradient of f is lambda times the gradient of g. All right, so going over here. Now, here's a little trick. We can use the chain rule in reverse to recognize that the gradient of g dot r prime of k is just the derivative with respect to k of g of r of k. Now what's g of r of k? Well, remember, r of k is a point on the level set g equals k. So by definition, g of r of k equals k. So this is lambda times d dk of k. And d dk of k is 1, so this whole thing is lambda. And that's the proof. I just show that d dk of m of k equals lambda. Isn't that cool? So now you know the secret of what Lagrange multipliers really mean.